Hi, my name is Pablo Alindo.
And my name is Łukasz Langa.
And this is the core.py podcast, an unpublished podcast where we discuss the internals of CPYTHON and our adventures in making a new version of your favorite programming language.
Well, this time I am already sitting on my bags, leaving for EuroPython tomorrow. So
EuroPython, me too.
Yeah, last minute episode.
What a coincidence!
Yes,
what a coincidence!
Let's just make it happen before we leave for Prague.
Nice.
Talk about the first major new feature of Python 3.15. Huh?
I think it's going to be the major feature of Python 3.15. Who knows?
Well, we'll see about that, but it is definitely already a major one.
Yes. What is the major feature? We are, of course, talking about...
adding a profiler to the standard library.
Oh, I thought you meant like adding a new parameter to the email module.
Yes,
the email module, Barry. We know where you are listening, Barry. The email module, the most popular module on the planet.
No, but like we are adding a profiler to the standard library
Very exciting.
We only had two before. So like that's not enough. Like we need to have more.
So, people will remember me like the duplicator or the triplicator because like how many parsers do we have in the standard library right now? We have like, we have less parsers now because we kill leave 2 to 3, but like we have a bunch of parsers, right? Like we at least have like, okay. So we have the peg parser and then we have the peg parser that generates Python. We have 2 parsers now. We are down from 4 to 2.
Yes,
or probably even 5.
So you're the deduplicator, but like over time.
Because the worst case was when we have the peg parser, the Python peg parser, then we have the parser module, then we have the lib223 module, and then the old parser. That was something.
Yes, that was 3.9. 3.9 had it all.
Oh, are you feeling sad about 3.9? Are you nostalgic?
No, it was a good version. Like the parser transition went really smoothly for how big it was internally. And it's still alive as a version until October. So we might still need to release at least one more. Like we'll talk about this a little later in the episode.
3.9. Y su puedo pensar 3.0.
Yeah.
Nice. That was a nice feature. But now we are going. We change from parsers to profilers. Both start with P, like Pablo. Wow, maybe that's the common denominator of what Pablo.
This is why you chose Python in the first place. I get it now.
Okay. That was a good one. All right. So yes, profilers. So why we care about having more profiler Łukasz?
Well, first of all, I didn't know we do. Like I was not extremely happy with the ones we had in the standard library, but I made do with them. So there were already 2, and both of them were in this sort of style of profiler that's called a tracing profiler, which is essentially an automated debugger backtrace collector, right? So when you have a debugger, what you can do with it, you can just say breakpoint and like stop your program at a given moment in time, and then just say, tell me the traceback of what is happening right now. And with cProfile, which is our faster version of the tracing profiler, you could look at the main thread of your application, and this one thread would be saying, I'm doing this at this particular moment in time. With the Python version, you could look at more than just one thread. But as I said, like it's like you stopping a debugger at a given moment in time and asking for a backtrace, but many, many times over. And when you're doing this, you can record where Python is over time in the moments where you're stopping, when you're tracing. And that way, just collect like a kind of view of the running application so that you know where time is spent. And the more time is spent in a particular place, you're going to have data that shows this, that there's going to be longer time spent there. And hence profiling. That's why we call it profiling. And tracing profilers in particular are like so well automated that they can stop your program at every function call and at every return, meaning they are pretty deterministic, right? They are going to give you the actual full information on what is happening with your program.
But you mentioned interesting. You mentioned that we have two profilers. So why do we have two profilers? Where are these two profilers?
Well, they one is called just profile, and it's just like profile.py, and that's the pure Python version. It is already, and in fact, like, it allows you to just like see that there is a cProfile there too, like whatnot. But like, yeah, like that's the pure Python version. And then there is a separate module called lowercase c, uppercase p profile. And like,
this is fucking crazy, man. Like, this is one of the things that when you come into Python and then it's like, oh, I just need a profiler. And then like a bunch of hooded people comes into your room and is like, hey, psst, you need to use this cProfile. It's like, what is the C about? Silence. But sure, it says that there is no such module as cProfile. Stupid person. It's uppercase.
yes,
Right? You just fuck it up.
uppercase
It's wrong letter. Like, what the fuck is going on? And like, what is this C, Łukasz? C is because the C language.
Yes.
The illegal language.
Exactly.
It's an implementation detail. It's an implementation detail that has surface to a letter that is very annoying because why is uppercase? It's horrendous. And profile, you say, oh yeah, you just say like in a nonchalant way, like, oh, it's the Python one. The Python one, man, this is dinosaur era shit. I'm checking the blame of this file, and like the average line age is 25 years old, 34 years old. Like, dude, the import sys, obviously, the profile imports a bunch of shit.
Yes.
So the import sys line is from the first commit ever, 34 years old, initial revision by Guido van Rossum. This is what we're talking about here, right?
Wow.
Amazing. Do you know the last time this file was touched? It was touched by Mario Corchero
Bloomberg Mario.
to add a -m option to profiler modules. So you could call this as Python -m profile.
Yeah.
Well, technically, it was also touched by who is this guy? Well, someone, just because there was some pipe error, but that's it. Like, the real change is like Mario Corchero, and then the rest is like 24-year-old like Tim Peters kind of thing. Jesus, man, like, this is old. It's very old and slow because like Python
yes, it is
like
slow because it is in Python. It is still, I think, if it's so slow and it's so old, as you said, like, then it's still probably using systrace or like settrace, right? Like, it was never converted.
Well,
to,
no, it's using settrace, but
669.
now that is very bad because like it's Python based. So now this thing is unoptimizing your code.
Yes.
Because like when you create the frames, it needs to instantiate the Python object for the frame, which we do never do. So like technically, you profile with this file, it's unprofiling your code. It's the unprofile.
Yes, so it is actually lying to you because it is giving you different information than you would get just running your program. That is actually a problem with tracing profilers in general to some extent anyway. The reason why cProfile was created in the first place was that Python-based profiling was just so slow compared to like regular code execution. So cProfile was the attempt, somewhat successful, to make this overhead lower. And in 2023, with like PEP 669 and with sys.monitoring, like Tiangawa actually like made cProfile support those new APIs, so it became even faster then. But even with those updates, cProfile, first of all, only can profile one thread for you, but mostly it still maintains its high overhead. So you cannot just like run it forever and just profile applications that you're interested in at a given moment in time in production because the overhead is too big. Like, it can affect performance in very unreasonable ways.
Can you guess the overhead of this thing? I measure it.
So I don't know right now, but I know like just
what is your gut telling you? What is your gut telling you?
Yeah, like it is very similar to what you're getting when you're, for example, running code coverage and so on. So like for this, it's usually like 8 to 10 times slower than what you're like having without running it.
7.3 is the measurement I gave with like some random shit. So yes.
What was the number you said?
7.3 times slower.
Whoa, okay, so I was pretty close then.
I mean, it's not technically coverage because coverage covers every single line and it needs to like do a bit more. This is just a function enters and exit, but like the whole I'm optimizing.
Which is why I said like a higher number, but like, yeah, like still almost same order of magnitude-ish, right? Like, kind of, yeah, it's like seven times slower. That is a lot. That is sacrificing a lot.
Right. So that is bad. And dear listeners, this will become an interesting problem later in the episode. So, like grab this, put it into your backpacks. It will become useful later. So sampling profilers, so avoid the profile module. Bad. All dinosaur era stuff. Use the horribly named cProfile. Again, remember this fact. Okay, so tracing profilers, no bueno. Maybe cProfile, uppercase P, lowercase c is good, but like... But it's still bad, right? Because like have some overhead, maybe not 7.3 times, but like maybe less, but like it's still there, not great because it runs in the same process. That's kind of bad, right? But there is a better word, Łukasz Langa. What is the solution?
Well,
the solution is not to run in the same process because of course, quantum mechanics tells you that if you observe the thing changes. So don't observe the thing. Well, I mean, okay, bad metaphor. You're observing it from a different place. You're observing with a telescope. So don't be on the thing that runs. If you are profiling a program, don't do it from the program itself because like that is like you're altering the world. No, bad idea. So a better idea is to use this thing called sampling profilers, which it could be a very confusing situation because you technically could have a sampling profiler from within the process.
Yeah.
But normally that's stupid. There are some. Okay, I will not name names.
But there are also very like questionable sampling profilers that are sampling
but we shouldn't
outside
name the names. We shouldn't name the names. No. We shouldn't do this. No.
Okay. If you don't want to name names, then like
we won't get the enemies.
I will do that in my private podcast. And no, I don't have a private podcast. I will, but I can speak to you like live in person at EuroPython and actually name names then. So if you're really curious, like which names we're not naming right now, like come to
us.
Prague.
We will reveal it. Actually, we will leave an Easter egg. If you really, really want to know, you will be able to know by listening to the podcast very attentively. And we just say that. We will figure out how to do that later.
Okay.
All right. Anyway, sampling profilers. Sampling profilers are kind of better because instead of like going and recording every single function call that you make, imagine that you do a lot of them, like that's bad. So instead of this, every time they kind of like look at the program and say like, what are you doing? And then it just records what it's doing, like the stack trace, like okay, this function is calling this function and blah blah. And then like it waits like a specific amount of time that's called the sample rate, and then it asks you again, and then again, and then again. And the idea is that if you do this enough times by the power of statistics, then you can know what are the slowest functions. You cannot know how many times every function was called. Because you cannot, but you can know which are the slowest functions because hopefully if you interrupt the program many times, only the slowest functions will appear all the time in those samples.
Yes, and you know what is fascinating to me about this? That this is literally signal processing. We are looking from the outside at a process and looking at its signal, sampling it at a sample rate, as you said yourself, let's say of 1000 hertz, meaning we are sampling it 1000 times per second. Thanks to the Nyquist theorem, we know that we can only sample signal up to the half of our sample rate, so up to 500 hertz. And this is actually useful for us because we know that this gives us a lower bound of how short a function can be for us to see it. And in this particular case, half of 1000 hertz is going to be 500 hertz, so that's 2 milliseconds. So if there are any functions in our program that are shorter than that, we might be missing it due to our sampling, due to how we are sampling it. But that is fine actually, right? Like this is okay because if you are sampling, you are mostly interested in what is my process doing? Where is it spending all this time? And functions that are super short are very rarely the cause of slowdowns. You're typically going to see one function over very, very, very many samples because the process spends a lot of time in that.
I must do this, Łukasz Langa. pedantic Pablo is here.
Let's go.
So the Nyquist theorem, very well explained, and Nyquist theorem, but you make a small mistake that we cannot forget.
First time. I don't think I've ever made
that mistake. The theorem is
before.
not only called Nyquist theorem, it's Nyquist what? There's two guys there.
Oh, I'm sorry. Yes.
Nyquist-Shannon theory. Whoa, theorem. Nyquist-Shannon. It's not Mark Shannon, different Shannon. But you see, the Shannons are a very popular brand. It's
nice.
Nyquist-Shannon sampling theorem. Very good, very good. And now, by the power of karma, you should censor yourself. And when you start talking about Nyquist theorem, you should slowly fade your explanation, and then we'll have fun. We'll have a lot of fun. Okay.
Well. Yes.
5 minutes later.
So this is kind of the same thing, except that audio doesn't have back traces, and profilers need back traces. So that's actually a bit annoying to get. But yes, that's the idea. The idea is that you sample the thing with some math, and then you use the math, and that's it. So yes, so the idea is okay, so we have tracing and we have samplers. So where is the sampler and profiler in the standard library? There is no sampling profiler in the standard library until now. Now there is one.
Well, so why do you want one in the standard library? Because of very selfish reasons. So I mean, we respect our users, of course, but
no. What do you mean?
Not about the users, it's about ourselves.
That's not the main reason.
We do it for
no.
What are you saying? No, we want to have a profiler that works with the Python version that we're working on, which is never the case for third-party
that's
profilers.
What you want. That's what you want. But the main thing is that this is the only profiler that is worth it. Because any tracing profiler, tracing profilers will tell you number of calls, but that is very, very, very not the case that you normally want. You want a bunch, when you want a profiler, you want a bunch of features that are really important. One, you don't want to modify the running application. You want to measure what runs. So if you run your application, you don't want it to be slow just because you're profiling it. That's one thing.
Yes.
The second thing is that you want to be able to have super high statistics, because now you can do a bunch of other things with those things more than just the profiler thing. And third, you want to be able to also run this on production. Because that's the whole deal of these things at the end of the time.
All of the things that you're saying are true, but a third-party profiler can reasonably provide this for us, even for already existing versions of Python.
That's what you say. Okay, interesting. Yes and no. For instance, the problem with third-party profilers is that they need to reverse engineer what we do in the standard library, which is we do.
Not always, though. That is not true. You yourself added the first JIT of CPython, right? Just so that perf as a profiler actually worked with CPython. So that is a third-party profiler.
Yes, I did that. Oh man, that's a different profiler as well. Maybe we have 5 profilers. Jesus. Okay. And perf has 2 modes, so maybe 6. Well, okay. Yes. Okay, yes, but that only works on Linux.
True. That's true.
Not anymore, by the way. Oh, whoa! What's going on? Okay, no, that's the beer of the week. We will talk later. Yeah. But spoiler. Now it's better.
Okay.
Okay. Yes, but yes, but no, because also okay. Interesting. So the perf one, even if you focus on the perf one allows you to have it is the mega profiler. So but allows you to have C calls and Python calls, as you very well know, right?
Sure.
That involves a fuck ton of data. This is a lot, so you cannot run it all the time. You cannot, because it's a lot of data and it's very tricky to get right, because all the native calls and whatnot. This is just a Python only profiler we're talking about here. Just Python, no C, nothing, just Python. So we just want Python. That's what we want. And then you want to create different things like flame graphs or p-stats or whatnot. So yes, technically you could already do this with the other things I did. But it's not that I just want to every 2 months create a new profiler. This is different. This is just for Python, so we can specialize it, and people don't need a nuclear reactor to profiler applications. Perf is big boy profiler, but this is medium boy profiler or small boy profiler or girl. We don't make distinctions here or unspecified. But like this is different. Okay, but you particularly, Łukasz Langa, you particularly, what you're saying that you are particularly excited because you can use it with the running version, which is also, by the way, an interesting thing, because if you rely on the third-party packages to add support for the new versions of CPython, then there is a period of time when nobody can profile the new version of Python.
There is a lag, of course, yes, and with a built-in one. No.
But also, the main reason as well that we want this on the standard library is that it allows, like, because these third-party profilers need to reverse engineer what CPython is doing.
Yes.
Right? And they do this after the fact.
Yeah.
But a lot of the optimization that we can do in these profilers, like, it's good to synchronize with something. So first, we provide as a reference implementation for these things. So we ensure that these profilers are not going to break with new versions. Because like we have one in the standard library, so you can just do that, and we know it works. And the other thing is that now, because this relies a lot on knowing what CPython itself is doing and the nitty-gritty details, we can know that we can add a bunch of optimizations on Python that prepares the profiler for doing that. So that all those third-party profilers that are even more powerful in different ways could leverage these optimizations instead of trying to, like, deal with the fact that we change the Python interpreter in a way that makes them slow. But I know that you are mostly excited because you can profile PyRepo. Yes.
Yeah.
Yes. But don't lie to our listeners. This is a very exciting thing.
Oh, I know it's going to be exciting for them, but I'm just saying, like, kind of, it is like dog fooding of the best sort.
Yes. So dear listeners, this is what happened. Łukasz Langa was feeling sad in his room because he was optimizing the color REPL. He was very excited about this color REPL thing, like that everybody loves. Like, that was the more cheer string casting announcement on PyCon US. The color of the REPL of Łukasz Langa. Okay, so he was profiling like a bunch of things, because if you recall from previous episodes, I gave him some exquisite ideas of how to make this. That apparently they were not that exquisite; they were half exquisite or quarter exquisite. But anyway, so Łukasz was trying to profile the thing, and Łukasz Langa found himself in a big problem because he couldn't profile 314.
Yeah.
Because there is no profiler that works with 314. Well, I mean, .profile or .cProfile, which are like not fully great because, like, different reasons. So what did you have to do, Łukasz Langa, to be able to profile it properly?
Well, at first I did start with cProfile and just did that, like a bunch of that, but it's like not perfect for a bunch of reasons. So then I just like copied what I was doing to just Python 3.13 because
disgusting.
Yes,
already disgusting.
PyRepo is in
disgusting.
Python, so you can actually, like, compare it to an older version with minimal changes. There are some changes necessary, but like not many. Like, then I was profiling on an older version.
Listen to this, dear listeners. This poor man here had to copy like a peasant this version of his new flashy code to an old version of Python. He had to backport it just to be able to profile it.
Yeah.
Is this what you want for your children? Is this what you want from your children? No. Your children should be able to profile on the latest version on day one with, like, the profiler that you deserve. And this is what we are adding to the standard library. So Łukasz Langa can finally has his dignity. And he can profile on 314.
So now, like, all slowness of PyRepo will be purely my fault, no longer the tooling fault.
All right. True.
So how does the sampling profiler even work?
Okay, yes. So the idea of the sampling profiler is that it's very simple. It has a magic, and the magic is able to, from a different process, it's able to introspect the Python interpreter. We will explain how in a second, but it is going to be able to introspect the Python interpreter, and it is going to be able to tell you, like, what is the stack trace by copying memory from the other process. So it just goes to the other process, it just copies a bunch of raw bytes, and by the power of magic, it interprets those bytes in a stack, and it will tell you what functions are being called at that particular time. And then you basically call it in a loop.
Yep.
That's it. That's the whole thing. I mean, devil in the details and whatnot. But so how to make a profiler faster? Well, you just make that function that magically copies memory from the other process very fast, and that's it. You just call it in a loop, and normally you don't want to run it at full speed all the time because that's going to burn your CPU. So you want to have something called the sample rate. So you can decide to sample like maybe 100 times a second or 300 times a second or something like that, right? But obviously,
so when you started out, like, what was that rate when you first started working on this?
I started to work with this with Laszlo, which is doing the front end part on PyCon, and basically we already have this machinery, right? Because why we have this machinery, Łukasz?
Well, for remote debugging and like for like external inspection, like initially I think like you had it for like memory and other tooling that just looks like from.
Well, I just hide so Markdown doesn't break the profilers on every release.
Yes, right. But like that machinery was there. Like, and for AsyncIO tools, like that's what we actually exposed to users before talking about the profiler, right?
Right. So now, but I said, okay, so we have this test that is able to prove that a profiler works. So we don't break the profiler. So we should be able to have a profiler, like exactly. It's the same thing, except that, oh no. So we started to do it, and then the plan is like, okay, Laszlo, you will work on the front end part, which is like the part that people will use. You call it, and he gets the samples, he does the math, like non-trivial stuff, very very interesting. And then I say I will just focus on making this function faster because the function is there, it just needs to be faster. Do you know the original? We are going to use hertz. So a hertz is samples per second. Like how many times? Like 3 hertz is that you're sampling 3 times per second, right? How many hertz?
Well, I don't know, like 1,000.
3. 3 hertz.
What?
3 hertz. Wow. Well, not good. This is the max sampler, right? So this is full speed, 3 hertz.
Oh,
and I was
full
like,
speed.
Jesus fucking Christ.
Okay.
So I use a profiler to profile the profiler, except that this is C code, so I have to use a cProfiler. And because I was using my macOS laptop and I didn't have access to my Linux box, which is normally where I develop, I had to learn how to use instruments, which is this like disgustingly made mega profiler that macOS has. So the technology, exquisite, like really impressive. The UI, disgusting.
You don't like
disgusting.
It?
Yeah, because do you know how it works? You need to it's a kind of like system thing. So you can sample everything at once, very powerful. But if you just want to sample one profile, do you know how you select it? Instead of writing the PID in a box, you click like a drop down, and the drop down will show you all the processes on the fucking machine, and then you scroll the drop down until you see yours, which by the way is not displayed with arguments. So you will have 6 ones called Python. And you need to know magically which one it is. It will show you the PID, but that's it. So you scroll across hundreds of processes until you find yours, and then you click and you click record. That's how it's supposed to work. It's disgusting.
That is weird, yeah.
Yes. It's horrible. Apple people, please, just a feel for the PID. It's not that hard, right? Like, and you already have the 99% done. All right. So I use instruments, and I discovered that we were doing a lot of very stupid shit. For instance, we were resolving the macOS task on every single invocation. Very slow thing. Like you don't need to know what that means, but like it's very slow, very stupid. You just need to resolve it once because the task is not going to like magically change because it can disappear, but like that's it. So yes. So we went. So the first day we went from 3 hertz to I think it was like 1,000 hertz or something like that. Yeah, quite crazy. And the second day,
then.
Yeah. I mean, that's already respectable shit.
Yeah.
The second day, I managed to get it to 10,000 hertz. Wow, 10,000 hertz. That's
10
quite
kilohertz.
cool.
That is already yes. You already sub a millisecond.
So that was the limit of like not being stupid. So just by not being stupid, I could get to 10,000 hertz. And then I said, okay, now the real optimizations are coming in. So I started to put optimization, not just like optimizing in the sense that not doing weird shit. It's just like now I'm like thinking about like how can I make this faster. So I started doing a bunch of ones like optimizations that make sense, leveraging the structure that we already have. So for instance, instead of copying, so these are just some examples, right? So instead of copying all the frames all the time, I'm copying the backend storage of the frames, which by the way is just a very common thing that third-party profiles do anyway. So I just copy the memory. So I just need to copy like the memory in one chunk, and then I know all the frames will be in those chunks. So with all of these existing optimizations, I could bring them to, I think it was 300,000 hertz. But then I said, okay, but I'm now in control of the interpreter, so I can do more things than anyone else. So I added some super tiny like flags in different places, so I can know, for instance, like if I can have caches, because like for instance when you're copying code objects from the process, like name of functions and things like that, those are not going to change all the time. They can change, but they are not going to change all the time. Like if you have a function in a file called profile.py, for instance, or whatever. That function is going away because it's there. It's like function foo on file profile.py, and like the name of the file and the name of the functions are probably going to stay there for the whole program.
Yep.
You cannot assume this. Because it's possible that someone creates like a lambda or something, or like a function inside a function, or a dynamic thing,
right?
And then it destroys that, and now something reuses the same address. So you cannot just assume between samples that the functions will be called the same. So some profiles actually caches the name of the functions. That's wrong, because you can totally destroy it and reuse the pointer. Like, that's wrong. You shouldn't do this. And as you know, in the standard library, we very much care about correctness. So I won't do the wrong thing. But I could modify the interpreter to tell me when the code objects have changed. So I know when I can invalidate.
So you can invalidate the cache. So you can have a cache with invalidation.
Yes, and I have a very smart cache.
Perfection.
Very smart cache that I won't go into details because it's quite complicated. But
nice.
With the smart cache, and after like a lot of days of like suffering and whatnot, and some memory tricks, because like now I'm using like this batch calls and whatnot, I could reach, it's just in very specific simple cases, but like that is still very impressive, 1 megahertz. 1 megahertz.
Million
1
hertz.
million hertz. Wow. This is amazing.
Not even dogs can hear that high.
I don't fucking know what you're talking about. Okay, yeah, that sounds like a big number. Dude, it's a big thing because 1 megahertz is like, what is the sampling rate of 1 megahertz, Łukasz?
1 microsecond.
Microsecond, exactly. It's 1 microsecond. How much time does a system call on average takes?
Like a few actual microseconds.
Yes, exactly. 3 on average on modern systems. I mean, it can take less depending on the system call, and some system calls.
So you reach the physical limit of
this is the physical limit, my dears. Yes, the physical limit. Exactly. Yes. So you probably can make it faster with some modifications that I'm also doing, and that will hopefully be in 3.15. Like use specific memory chunks for all these things, all the memory that I care and whatnot. But like, that's unclear if it's going to be better, by the way. But this is the physical limit, 1 megahertz. By the way, you don't need you technically don't need 1 megahertz, right? Like, just to be absolutely clear. And 1 megahertz is the absolute maximum, in the sense that if you have like a program that has 900 frames, it's not going to sample at 1 megahertz. Like, that's just to be clear. But like, this is proportional. So like, if I can sample the easy case at 1 megahertz, then I can sample this, like the hard case at faster rate, right? Also, very important, if you have multiple threads, then you divide that megahertz by the number of threads.
Yeah, of course.
Because in the same sample, now you just need to sample more things, right? In non-free threaded world, that is not technically the case, because you could only sample the thread that has the guild.
Exactly.
Very smart optimization. But in the free threaded world, that's it. Like, every thread is doing different things. So like, better to sample fast, because you now divide by the number of threads, which is, now it's not 1 megahertz, now it's 1 divided by the n megahertz. Okay.
Yeah, but like the free threaded thing like wasn't just like, like recording multiple trace bags, because they're running now. Like, it is actually pretty complicated to do, right?
Indeed.
Like, these days, like even Python with the GIL is no longer like trivial, like since like a few versions ago, right? Because historically,
due to the Nyquist Shannon interjection,
due to the Shannon interjection.
Well, more people than Shannon.
Traditionally, what we had was, whenever you ran a Python function, CPython was calling a bunch of functions to do that. So you could very predictably see this pattern of functions in a C stack trace. So just following the stack up, you could see everything that was happening in a Python program and like pretty easily map one thing to the other. But things change, and what was it, 3.11 or 3.12, where we no longer now like always create C-level like function calls in ceval-c. What is happening is, if a Python function is calling directly another Python function, we can just update structures in the memory that are like frames, but they're not C-level frames.
That was a Galindo-Shannon optimization.
Nice, very nice. So this made it pretty fast, right? Plus, it allowed us to have much deeper recursion limits, because now you're not tied to the system-level C stack. but it makes it harder for us to reconstruct stack trace.
Correct.
And that's only for one thread. If you have the GIL, like that's where you are, because you can only run one thread at a time. Even if you define multiple ones in your program, there is a place in the memory where you can check, okay, like this thread is running at this moment, and because of the GIL, you know that's the only one. So you only need to copy one stack trace using all these shenanigans. But when you have a free-threaded build, multiple threads can execute at the same time. And as you know, the fast Python team was faced with a challenge when free threading came around, because all of this sort of specialization, JITs, and a lot of these other optimizations that we're talking about were sort of relying on the fact that there was a GIL before. So to avoid having to recreate a lock for this purpose, like from a global lock to a local lock, just for making sure that all your specializations still work on different threads, there was a new solution, which is typically don't lock, make things thread local. And now we, in fact, have thread local bytecode. We call that TLBC for short. Yes, and this is to avoid locking overhead during bytecode dispatch. So every thread may use a dedicated bytecode array essentially for their own things. So now you essentially have three levels. If you look at our implementation, there is going to be this sort of like canonical bytecode, which is the one that is like clean and not optimized at all. That's the sort of raw one. Then you're going to have the main thread one that might have optimizations. And if you spawn any other threads, they're going to have their own bytecode as well. So this sort of profiler that you create to make it possible to follow all of those stack traces right now, it needs to understand TLBC. It needs to know how to get back of and see like all of this dispatch. And why? You're asking like that is a little weird, because all we need is stack traces. So why are we looking at bytecode again? Well, because you need to map things back to line numbers, right? You need to essentially
very important.
Yeah, you need to present data in a format that humans can understand. Otherwise, it would be pretty confusing.
By the way, this is another advantage I just figured out. This is another advantage of the sampling profiler, because the tracing profiler, because it only knows function enters and function exits, it cannot know the line number that is being currently executed. So the leaf line numbers are missing.
That is true. That is true.
Right, but we don't miss them now, because when you take a sample, you just know what it is right now. So,
yes, but like it's statistical, but that is good enough. If you have a million samples per second,
1 million samples per second.
That's good enough. Like you will see what your like bell curve of like lines per execution of even very short functions. Where do they hit? Where do you usually wait? Yeah.
Right. So indeed, and this is a bit annoying, because all this like mega machinery to resolve the tilbuk arrays is just to get the line numbers. And the reason this works is because the way you get the line numbers is that Python knows, like the line number is a kind of like expensive thing to know, because like Python doesn't know what a line number is. Python just knows instructions. Like, what instruction I'm executing now is instruction number 30, and now instruction number 31. Like, what line number is this? So to know the line number, you need to execute the Shannon spell, which is this like magic function that will grab the current instruction offset, like instruction number 34. It will grab a bunch of magic data that is like packed there in the call object, the line number table, and then it will compute a bunch of stuff. Basically, it will do a bunch of math with the compressed line numbers, and it will tell you what is the line number. So you just need two pieces to know the line numbers. You need to know the magic data, and then you need to know the instruction offset. But this is a problem, my dear, because Python also doesn't know the instruction offset. Python knows the instruction pointer. Well, Python and everything else, because that's how things work. So you want to know the instruction offset, you need to subtract the instruction pointer from the start of the bytecode array. But here's the problem. Every thread has a different start of the bytecode array. So just knowing the instruction pointer is not enough. You need to know from where it starts, like what is the beginning of the array. And that is thread local.
Yeah.
So now you're in the business of resolving all the thread local bullshit.
Plus, you cannot even run Mark Shannon's function, right? Because you are outside of process right now. So you need to recreate.
You need to recreate Mark
was
Shannon
doing.
function. But every profiler needs to
Yeah.
recreate Mark Shannon function. That is the Mark Shannon tax. that is the deal. Like every profiler needs to know this. So that's okay. It's fine. It's not that complicated. Man, it's enough complicated that if you run a 1 million hertz per hertz, then it appears on the profile. Like if you profile your profiler and then you say, okay, it's okay, 1 million, that's kind of cool, but can it do 2 million? Spoiler, no. But like if you know, like, okay, why are you doing now? 30% of the time the profile is running is Mark Shannon tax. Like it's just running Mark Shannon magic function, which by the way, just to be absolutely clear with everyone here, that's unavoidable because like the cost of not running that function is to have ginormous data for the line number arrays, and then your Python interpreter will use a lot of extra memory, and that's like a no-go. So yes, this is the optimal way, and it's just that now you need to uncompress that, and that's going to take CPU cycles, and that's it. But like it's very cool that is the limit of the profiler these days. 1 million. Okay. So yes. So we need to solve all these like just to know where the function pointers are. And now that you do that, you pay the Mark Shannon tax and you can know the line numbers. And it's very cool now because with the line numbers, you can do a bunch of things. For instance, if you have a ginormous function called main or run or whatever, very common on little scripts, for instance.
Yes.
Then cProfile will tell you shit because it doesn't resolve the line numbers. But the DC will tell you. Very cool.
But you know what this will not tell me?
Well, it will not tell you.
When I do like super profiling with this sort of thing, right? And I run an AsyncIO application, well, like a million like things per second. So that's amazing. But like I will do that, right? And I'm running.
How many times per second?
1 million times per second.
No, but I don't hear you. You're saying in a weird way that I cannot understand.
$1 million.
1 million.
1 million.
Okay, but I do this, and all it tells me is that the AsyncIO event loop is running, and it doesn't tell me
it's
anything
1 million
else.
times AsyncIO event loop.
Yes,
Bad.
it's amazing. So like that kind of sucks. Like I would like it to be like, you know, just as cool as our AsyncIO tools that tell us the tree of the tasks that are running, but for an actual profile, so like in time, so even better than what we have in AsyncIO tools.
Listen to me.
What?
Granted. Your wish is granted. This is because you were like, this profile is only good because we run it in the last version. No, it's only good because like it's awesome. It's the fastest profiler as of today. The fastest profiler because 1 million is at least around like between 7 times and an order of magnitude bigger than the rest of the world. Until everybody copies my optimizations and it's just the same. Who was first? Me, no, I was not first. I copied internal other optimizations, but then I added mine. Anyway, so yes, it's not only because we want to offer in the standard library the most exquisite profiler experience that's built in. It's because this will be the first out of process Python AsyncIO profiler. Out of process Python AsyncIO profiler, not in process, out of process. Very important because we will use the thing that we did before.
Yes.
In Python 3.14. Łukasz, tell us about this. Tell us about this. Like, why is this a thing? Why is this important?
So the problem with async code is that if you are running an AsyncIO application and you have multiple tasks at the same time, this is sort of like getting back to the world of the Gale, because this is cooperative multitasking. So at any given moment in time, there will only be a single one of those tasks executing. So if you don't have any magical AsyncIO support in your profiler, what you're going to see is, oh, there is a task running on the event loop right now. And that's all that you're going to see. You're not going to see where this task came from, so who is awaiting on it, and you will not see how many others there are. So like in traditional profiling, like, kind of this is both like gonna be very slow and affecting AsyncIO, but also you will not be able to reconstruct the, well, air quotes, async tracebacks, which are not actual stack traces, but they are just like a trees of who awaits on whom. And this is what you actually want to have, because otherwise you only just see like run until complete, and so on and so on. It gets worse actually, because plenty of AsyncIO things actually have some optimizations that to just do networking without creating like a coroutine in memory. So like a nice task object that we can look at. They are using lower level APIs. And for those, you cannot tell what is happening because nothing is happening, because even
just the event loop.
Not even like the event loop is doing anything. So you cannot see.
Oh, it's calling select. No?
Yeah, that's the thing. The select is outsourcing your waiting to the operating system. It's a syscall, right? And select is essentially, the contract is that if there is anything on my file descriptor, then the operating system will let us know, right? It'll tell us, okay, now there's something to read, or you can write to this file descriptor now, and so on.
Yes.
But until that happens, even if you do sampling profiling, you will just not see any activity because this is hidden by the kernel of the operating system from you. Like that, we are in fact waiting on something.
I have to say something. So do you know what is one of the most typical comments that people do when they tell us about Cordopy?
Yeah.
That they don't understand shit.
What?
That they say, you are very funny, but like we don't understand anything. So we need to introduce this thing. Like, how they solve this in movies, no?
No.
So in movies, they like there is the scientist character, and they explain things like.
And there's this new guy who doesn't know anything, so he asks questions.
Yeah. So exactly. So there is the funny but like stupid person. And then the scientist says like, yeah, we need to frambulate the frambulator, right? And then the guy is like, it will be like blowing up a big balloon. So we need that guy. So I'm going to be that guy. So okay. I'm going to. So you say a bunch of like very smart things, but I will tell you about like my experience, and then you will tell me why your smart things apply to my experience.
Okay.
So the other day at a place that I may or may not work, I was debugging this AsyncIO fast API. You see, I'm saying fast API. A lot of people use fast API, so now they feel connected to our story.
It's relatable.
So, and it was true. It was a fast API server. So I was using the fast API thing. And the fast API thing, it was very stupid because at the time I was trying to run it, it was just running one single request. So just not even multiple requests, just single request, right? Like very, very, very stupid. And it was just doing a bunch of like gets against URL, like fetch data from here, fetch data from there. And then it was fucking slow, like really slow. Like it was taking minutes. And then I said, okay, I will use a profiler. And then I use a profiler and I got shit, like nothing. It will tell me that all my program is slow because it's running like something called select. So why is this slow? Because like why is not telling me why it's slow?
So select, if you're running select, that just means you are, effectively polling it, asking it for like, hey, kernel, do I have anything that I can do stuff with? And the kernel mostly says no. Because if you profiled and select returns anything useful for you often, then you would see your processing appearing in the profile results. If you,
So then where is my application spending time?
Your application is spending time in waiting for networking. So either you have some issue with like an actual bandwidth. So you're trying to like, kind of send something that is huge and you're just waiting for it to like, kind of respond to you, or you are like hitting some external service that takes a long while to even start sending you any data, or you are waiting for DNS that is just like unreasonably slow for you, stuff like that.
But Łukasz, my application can be doing a lot of things. It's fetching all sorts of things. Which one is the slow one?
Oh, and that's the thing. You don't know. You don't see anything.
Sell me this pen. Sell me this pen.
Oh, sell me this pen. It's powered by AI.
Okay. Yeah. Now I want it. Pen code. All right, exactly. I want to know which one is low. And I couldn't.
So
I couldn't
we
because
didn't know. Yeah. Because yes, select doesn't tell you which one. Like, well, you're waiting on all of the ones that you registered, but like which
even if you know what are you waiting on, the thing that select is waiting on is the number 6.
Yes,
Like
exactly.
I'm waiting for 6. What is 6?
Oh, you can just do LSOF and like you can recover this information, but it's very
no,
very
because
annoying.
it will tell me a URL, but like my task is like very nicely described, like it has description. It's called
Yes,
like
exactly.
fetch blue blue blue
So
blue blue.
there is a disconnect. You would have
Yes,
to
yes.
have specific event loop support to like reconstruct
horrible.
this.
But it
But
sounds
this would
very
be like
complicated.
Mark
I just want
Shannon
to know.
tax, because from outside of process, you would have to reconstruct a big chunk of AsyncIO to be able to do this. That's terrible.
Man, but that sounds very complicated.
Yeah, it
Do you
does.
think someone will do it?
I think we sort of did a bunch of things for 3.14, and now like I think they're a good foundation to continue and actually make the profiler work for what people actually need.
Yes. So I did that. You did it actually. Well, sorry. You did the foundation. It was a very good foundation. People can
Like plus
watch
minus?
yes. People can watch certain talk about AsyncIO in PyCon US 2025
like a yellow
to know
talk.
more about like the story of this. But apart from Łukasz creating the most horrible data structure of the universe, I mean,
1 million? Rookie numbers.
yeah, rookie numbers. 2 to the power of n to the power of 2 complexity.
Yeah.
I would love to say that. Like, when you are doing an interview question, okay, this is good. But what is the complexity of your solution? Well, it's 2 to the power of n to the power of 2. But it runs in constant space. All right. It's just the constant space is all the universe. That's the constant space. It just requires all the universe. Okay, so yes, that was a very good foundation. I just have to modify. So we actually fixed for 3.14 the most horrible data structure of the universe, but like here it was another place when we were using the most horrible data structure of the universe, except that it was limited because it's just the current task. So I just modified it as well, and I added more optimizations on top of that. But now we can indeed sample AsyncIO programs, and we can sample in 2 fantastic, exquisite ways. So there is 2 questions that you may be asking to an AsyncIO program, Łukasz.
Yeah.
Question number 1.
What task is currently running?
Yes, like when you actually do things, Mr. AsyncIO program, what are the things that you are doing?
Yeah.
So that will help you identify, for instance, blocking code. Or like, like blocking code, for instance, because like you can see, okay. So my when AsyncIO is actually running something, most of the time it's running this bullshit thing. And you will say, but Pablo, but you could like get that information also with a normal profiler. Yes, but you will miss the coroutine, you see, because you will only get the event loop above your head. But with the AsyncIO thing, it will tell you, yes, you are running this blocking code, but also the task that is running your blocking code is this one. So now you can find it. It's cool. Okay, that's kind of cool. You can also know, like, what AsyncIO functions are not blocking, but they are still running most of the time. Very interesting question. But also, that is the current mode. But also you can run in all task mode or all mode, or like just give me all the info mode, which will tell you at every sample all the tasks that are waiting.
That is
and then
awesome.
You can finally know which tasks are blocking your thing, right? Because like now in my case of my fast API thing that was slow, it will tell me, well, dude, you have one task that is called download the thing. And that is taking a long time. So it's just waiting for download the thing. So I say, of course, because it's 2 terabytes of data.
Exactly.
So like over my modem connection. So that is the answer. And when you have a lot of requests, now you can know all sorts of things. If you name your task nicely, because obviously, like, to know what task is everything, you need to put names to your task.
Task 1.
Yes, task 1 is...
That's the default.
That's the event loop, right? But like, if you put names to your tasks, well, you should. Then, or your framework author should, then you will know a bunch of shit. For instance, you will know what request is creating the thing, like, or what request number, or what user, or what anything. So you know a bunch of like very cool things just by like doing that. And this is going to be revolutionary, because now you can like you can profile all the AsyncIO applications, and everything these days uses AsyncIO.
Yes.
All these MCP things, like fast API, blue, like everything is AsyncIO these days, and nothing profiles AsyncIO from a different program non-modified program. This is very important because you can do like a bunch of weird shit. Like you can monkey patch the internals of AsyncIO, and like that is disgusting. What this profiler does is that you have something running on production and modify pristine, exquisite application running there, and then you attach from a different process and modify. Amazing. And you don't make it slower. It's just runs full speed, and you profile from the other way. It's the holy grail. It's amazing. And it will be able to run in a AsyncIO mode. Exquisite. It is just exquisite. Fantastic.
So, like, I think about this, right? And like 1 million.
1 million.
Yes, 1 million samples per second. That sounds awesome, but
right. Your mileage may vary.
That still makes it possible sometimes for you to read memory in a way where if you're not blocking the other process, the process is going to change under you while you're copying memory. So is it possible in such a profiler that you're going to get like garbage data that is going to be inconsistent internally?
Yes.
So what is happening?
One of the challenges of these profilers, you need to detect, like you need to account for the fact that you can have a sample that changes under you. And
so what happens in that time? Like, because like some memory kind of pointers change, some data was overwritten and whatever. So like, what do you typically see?
So you don't see anything as a user because we just reject the sample. So the what happens is that we kind of like do the thing, and then we have some validation. So we cannot crash because we just copy garbage. So we need to validate that the garbage makes sense. So there is a bunch of code to validate the pointers, and the strings are strings, and we didn't copy bullshit. But it's possible. Particularly the classic example here is the frame change just changes under you. So you are copying one frame, and when you go to the color, then that's a different color, and then your frame now points to bullshit. So in that case, we detect that happened, and we reject the sample. So when you run the profiler, you can see a bunch of metrics if you want, and some of the metrics is like number of error samples. So error samples is like these cases. So
I see. Okay, so you report this.
Yes, exactly. Yes, so you will know. You can know a bunch of things. For instance, we print the statistics of the sample rate, the standard deviation of the sample rate. So you know how fast, because you tell us the sample rate that you wish. Like by default, I think it's 100 microseconds, just not to destroy your CPU, but like you can go as fast as 1 million. But then you tell us which one you want, and depending on the program, we may be able to keep that or not. So we will tell you if we are not able to keep up, because it takes us more time to take the samples than what you want. And the other thing that we tell you is like how many of those samples were error samples.
And typically, what is it that you're seeing? Like, what's the percentage of like samples that you need to throw away?
0.05 or something like that.
Whoa, okay, that's good. That's fine.
And that's when you sample. It's very interesting because if you sample at a very slow rate, it's very rare that you get a bad sample because you're sampling so rarely that normally just makes sense. But if you sample at a super fast rate, also makes sense because you're sampling much faster than what the program is changing. But there is a number in the middle when like your program is changing at the same speed you're sampling, which will change per program. So there is a balance between the sample rate. But in any case, normally we sample so fast in general, like the actual sample, like the act of taking the sample is so fast anyway, and we use caches when we can. So it's very rare that, like, normally these events are very rare. I mean, they can happen, but any profiler is subjected to this in any case. And the usually you will see anything is because like we don't use those samples for anything.
All right, so 3.15 is the first version that's gonna have it. So that's gonna be in like what, like next October? Well, not 20.
1 year.
Yeah, over 1 year. Like that is a long time.
Man, that's insane. The other day I was telling a contributor, yeah, your thing will be in October 2026, and they died. They said like.
So, okay, like when I started contributing, I was adding things to Python 3.2, and that was a version nobody was using because for the next like 6-7 years, people still on Python 2. So now that gonna have to wait like a year, like it's a little hard for me to just, like whip out my like tiniest violin, just like, oh, poor you. But still, like, poor me, I want to use it right now, like, kind of. So where do I find it? Like, I develop Python, so I don't care that it's not in a released version. So if I want to use it for PyRepo, like, where is it?
Yes, so we added this on their profile.sample. So now profile is a module.
But you just said like we shouldn't be using profile.
Yeah, it's very annoying.
But maybe you should call it cProfile sample.
Disgusting.
Maybe you should call it like Jeff.
No, actually, the profile has a name.
Yes?
Yes, you know the name?
No.
It's called Tachyon.
Tachyon.
know what a tachyon
Oh, yes, because like it's very speedy.
Yeah, exactly. So, dear listener, well, tell us what a tachyon is, Łukasz.
I don't know. It's physical. Like whatever I'm gonna say, like it's like it's gonna be
Pablo.
pedantic. Pablo says like, oh yeah, you were close, but no cigar. So I'm not gonna attempt it. Like I know it from science fiction games. So yeah, my knowledge is very minimal on this.
I mean, it's not like there is not a lot of physicality to it, but yes, like it's probably going to be very close to what you have in mind. So a tachyon is a hypothetical particle that goes faster than the speed of light. That's it.
Yeah. Okay, cool. So that's essentially what I would say. But
yes, like it doesn't even have. I mean, it has a bunch of weird shit, but like it's hypothetical. So like we don't even talk about tachyons as like outside science fiction because like when you do the math, it just tells you that there is three things like lower, at, and bigger, and like lower than the speed of light, that's mass. At the speed of light is photons, and then you need a name for the other one. So people call it tachyons, but like because it's hypothetical and we know that nothing goes faster than the speed of light, then we don't talk about it a lot. Like, but the math doesn't know. You know what I mean? Like there's nothing in the math that says this is illegal.
Right? I get it.
The only thing that the math tells you is that those three things are are in boundaries. So if you move lower than the speed of light, you cannot go at or bigger. Like you cannot just cross that boundary. If you move at the speed of light, you cannot go slower or faster. Like you always at the speed of light. And then you go faster than the speed of light, you cannot go slower or at the speed of light. Like that's what the math tells you. Like it's just three disconnected regions, but like that's it. So a tachyon is a particle that goes faster than the speed of light, and because this is very fast, because 1 million. Well, anyway, so what I want is to. So this is a very bad situation because it's confusing. Like you have profile, but you're not supposed to use profile, and then you have cProfile with kind of like it's a weird name, a very weird name, uppercase C uppercase P lowercase c, like whatever. And then you have profile.sample, which is like what you said, like are you supposed to use this kind of like confusing? So I said, okay, what do we should do? So I asked the steering council. What are the thoughts on this? And they say, well, like maybe what we can do is to have the profilers module, which by the way is good because there is no such a thing in PyPI, so we can take that. So we can take the profilers module and then deprecate the old one. I mean, not remove it because we cannot remove it, but like deprecate it, and then put profilers.sample and profilers.tracing. And when I see profile, the other is just aliases for them. And I want also an alias called profilers.tachyon because that's the name of the thing.
And profilers.deprecated, and that's going to be
deprecated. Profilers.shit. Okay.
Profilers.history.
Because we said before that like big modules, like big namespace modules like profilers require a PEP because you cannot just have a module anymore. Like that's illegal.
Yeah.
So probably we need a PEP here. So I don't know. I just need to know if I mean I will do it probably, but like that's the worst kind of PEP because it's a naming PEP, like where the whole point of the PEP is as the name, and everybody will have an opinion. No, let's call it like profilers maybe, or like.
No, profilers is a good name because it does not exist on PyPI.
I think
currently.
so. I think so. It's perfect. Like I mean, the idea by the way was Barry Warshaw. So Barry, you're listening. You are the guy. So it's a very good idea because like perfect. There is nothing called profilers. We can namespace, and there is precedence by the way because we have the compression module now when we namespace all the compression algorithms.
That's true.
Yes. That so it makes sense. It makes sense. It's a perfect match. But man, I will tell you, a lot of people have opinions. Which is fine, like that's how the community works, and nothing against that. It's just that normally when you have a technical PEP, your technical merits normally can they are the important fact, and like the name of the things is secondary. But this PEP is only about naming. So
yeah, I know.
Do you want a profiler? I mean, maybe I don't know. Maybe someone has a better idea, but like I couldn't think of a better idea than this. Like this is really good. I don't know. What do you think?
Jeff is better because it's just 4 letters.
Yeah. What? Jeff. Like, the people. Anyway, So that's it. Summary
It's
of
coming.
this. I'm very excited, man. I'm very excited. This is fantastic. It's the culmination of a lot of work. AsyncIO mode, fantastic. It's also built on the standard library, which is very important because
Yes.
Go. Everybody loves pProf. Everybody loves pProf. And there is also third-party profilers, but the pProf is in the standard library. It's really high quality. Everybody looks at excellent. You can reach. You need mega things and different visualizations. Then sure, you use a third-party one. But
Nice.
pProf is built enough. It will work immediately with other things. And also very important, it will provide a base for other third-party profilers to build on top of it, so they can know it works. Because right now they need to kind of fight against CPython, and every time we change something, they need to adapt. But now they have a reference implementation, so they know that this is going to be possible. And it's very important because in the modern world, performance is important. And this right now, I'm super excited because it's the fastest Python profiler on the planet by another magnitude almost.
Okay.
1 million. 1 million.
Perfection.
All right, cool. But now it's time to abandon the profiler war. All right. Okay, so I'm actually very excited about this. I have to say, I have a bunch of kudos for play people or whatnot. Okay, so you know that I'm into profilers as well, right? You know that I do profilers. This is something I do. All right, so I did this perf profiler integration in Python 3.12 and then 3.13, and that was very hard because it was the second JIT compiler, as Brand Booker liked to say. Very very rightful. He's right. The first one technically is the C types. Called something that just JIT compiles some trampoline, but anyway, that's bullshit, and it's a different library, so nobody did that in CPython. Anyway, so I did this perf integration, very complicated perf integration, and that will allow you to in Linux use the Linux perf profiler to profile your applications. That's the insane profiler. It will tell you all sorts of things, even what you had for breakfast and whatnot, but only works on Linux. So kind of bad, and but a bunch of magic things happen. A bunch of people are creating other profilers for C and C++ because having more profilers is better than having one profiler.
That's one of the exceptions where more is better.
Which is interesting because when I was at PyCon, I attended Lisandro's Nicolau, our good friend Lisandro's talk about free threaded and how you can deal with it. And one of the things they say is that you should profile your thing, because it will tell you have contention and whatnot, blah blah blah. And because this is C code, normally then you need to profile in combination with Python. They basically say, well, you use Pablo's thing among other things. But then instead of saying perf, I was confused because they didn't say use perf. No, they say use samply, and I was like, what? Yeah, so use samply. So samply is a different profiler that someone made in Rust, by the way, and it's just like perf. It just does the same thing. I mean, sorry, okay, perf does more, but the basics, which is what you want. And it's a very good profiler, man. I use it. Amazing.
Okay.
Fantastic.
Let's go samply.
Samply, yeah.
Mm-hmm.
So very cool, very simple. It uses the Firefox UX, so you can very nice. It's a very nice experience. Very nice, very good profiler, exquisitely made. And then I say, okay, that's kind of cool that you can also do this with samply. And you just use, it's kind of weird because you need to use the perf integration, but Samply knows how to use that, right?
Right.
And then I had this PR by
Canova.
Canova, but the name is
Nazim Khan
Altinova. Okay, so this person works with the author of Samply, which also appeared on the PR later. And then the PR is basically, they created an issue called, consider enable perf trampoline on macOS. And I was like, what do you mean? It just works on Linux. I mean, that was the problem, right? Because this is only activated on Linux. And they say, yeah, but Samply just also works on macOS and Windows. I was like, wow. And you can just use the same thing because Samply added support for the perf thing. It just mirrors it. So it uses the files that we create, not all information, just most of it. But you can it just works on macOS. And Marcus Stange, not Strange, Stange, the author of Samply, also appeared there. And it's like, we do this, we don't do the whole deal, but we do most of it. So you can just, by activating it and maybe changing here and there, you can just use it on macOS. And you can have almost the same mega experience because by default, it will give you all the native frames, all the C frames and whatnot, plus the Python frames.
Perfect.
It's amazing. And not only that, the Firefox UI when you inspect your profilers, is already prepared to deal with JavaScript JITs. So it's already prepared to distinguish just JavaScript frames from some native frames. And
so
it's
it
kind of a
already
bit
knows.
weird because
Okay.
they hack a bit and they tell the Firefox profiler that Python frames are JavaScript. So in the top left, there is these 3 tabs that you can check. One of them is like all code, the other is JavaScript, and the other is like something. But if you click JavaScript, it will only show you Python ones, which is kind of cool. So you can have literally like a mega profiler as well that can tell you your C extensions, also on macOS. And I was like, man, this is so cool. And apparently the Windows people also want this for not sampling, but their other thing. But probably sampling can use it as well. Man, amazing. Isn't it cool?
It is very cool.
And then we discovered a bunch of things. So it was not fully ready. Why not? Because like it worked on AR64, which, as you know, is the platform where macOS matters. But on Linux x86 64, it was kind of like flaky, and the reason it was flaky is because my perf JIT code was not preserving frame pointers on the code. The reason this was the case, by the way, is because perf runs in 2 modes. One of them is frame pointer based, so this only works if you compile everything with frame pointers, which nobody does because it's lower. And then I added this mega version called the perf JIT, which implements the mega stupidly crazy you will die version of everything, which creates like full debug information, dwarf, the file is crazy. And then perf uses the information that I put there to know how to go across the JIT compile code that I do. So that's fine. But Samply doesn't use any of this. Samply just goes across it. If you have frame pointers or you don't have it. And the way it does it is that when you reach the JIT code, it tries to use frame pointers only there.
I see.
Right? Only there. So they needed me to have frame pointers in the JIT code, even if we don't have frame pointers everywhere else, right? So that's so I started adding that. And then I said, well, I mean, this needs this other modification. And then I said, oh, this other modification. And then like everything started failing on AR64. So I discovered that I have like 3 bugs because the dwarf that I was creating for AR64 was like suspicious. I mean, you just have a little bug. It's just like an offset. And then like, man, doesn't your head hurts when you reason about offsets? Like an alignment? Like that's a very confusing thing. So I was aligning all the code, like all the instructions at 16 bytes, right? That's kind of cool. But then the code itself, the JIT code is 20 bytes. So then what is the alignment of that? If I'm aligning at 16 and the code is 20, what is the next 16 multiple?
32.
32. So all the code was in boundaries of 32. But I was aligning the kind of like the pointers to 16. So what was happening is that I was landing the pointers in the fucking middle of the code, not in the beginning. So that was confusing. Even if you check both the addresses, those addresses are obviously divisible by 16, but it's just the offset, the star offset is different.
Makes sense.
Bad. So you need to take the bigger number for alignment. Well, anyway, there was a bunch of like, so what originally the PR was originally called like add frame pointers for x86 64. And now the PR is called Fix Several Problems on Perf Trampolines for x86 64 and AX64. So, but now, man, the file is very complicated and it's full of magic, but it's exquisitely, man. I put so many comments on this file in previous installments, but also here. I put ASCII diagrams. Like, man, maintaining this now is a breeze, and everything now is dynamic. So there is no magic numbers in the code. So I'm very happy. This was super painful, man. Like this was super painful. Every time I need to deal with this nonsense is super painful. But man, like I'm very happy. And now in Python 3.15, maybe Hugo wants, which I doubt because they wanted this for 3.14. I say, well, no. But then I said, well, you convince Hugo, maybe. I'm very unlikely because we're in beta 4.
Yes, well, after beta 4.
Yeah, but technically this is if def. So it's just new behavior on a new platform. So it shouldn't affect the previous platform. The other is a bug fix. So I don't know. There is like 1% that Hugo humorous. To be honest, like as a release manager, I probably wouldn't allow it. So maybe probably he wouldn't allow it either. But like I just asked the question because they wanted the possibility. So I don't know. I just maybe, but like if not, like this will be on 3.15. The only reason to have it on 3.14, by the way, is that then people can profile free-threaded Python a bit better in macOS as well.
Right.
So maybe it's a justification.
Yeah,
for
like
that,
if I was only like selfish, like I would be like, yeah, let's do it. But if I also was selfish with a different hat, with a release manager hat, I would be like, well, we didn't have enough time to test it before we really scanned it. And that's true, right? Because now the next version, the first version in which this would appear is RC1. That is cutting it too close.
Well, I will tell you something. It's not the only thing that only appears in RC1.
I get it.
Not look at me. It's not me, I think. But just saying. Precedence and whatnot. Well, anyway.
I mean, I can argue both ways, is what I'm saying.
Yes. I mean, I don't know what I will choose, to be honest. But that is very excited. So Git compilers, my work that only was for perf now works on macOS. Man, this is such a exciting time. I love it. Okay, what do you have for us, Łukasz Schlange?
Well, Pablo actually, Marta Gomez, E. Durbin, Jacob Coffey, and I made a new thing for Python core development, which isn't really a feature that is like super exciting for users of Python, I guess. Maybe indirectly because of what it enables. But it is pretty fun for us because it allows us better visibility into what is changing in Python over time. That thing is called memory.python.org and is a new service that allows us to see how usage of memory changes over versions of Python. And that's not only like big versions like the released ones that you see installers for, but essentially every commit might be tested. So you might have very granular tests of memory and see, for particular benchmarks, whether the memory usage stayed the same or got worse. You can have multiple configurations of environments in which you're testing. So we can test the optimized version with PGO, with no PGO. We can test with JIT enabled, disabled. We can check with the GAL, with the GAL disabled, and so on and so on. So there can be very many worker configurations, and all of them sort of work somewhere in the cloud. And the cool thing about memory benchmarks in particular, that unlike time-based performance benchmarks, they can be successfully run in virtualized environments because you are not really bound to the fact that the hypervisor suddenly will now steal some wall clock time from under you. We don't care about that. The memory usage is the memory usage, right? So we can just as well just use GitHub Actions runners for this, which is essentially what we're doing right now. There's going to be more servers that we're going to be set up for us like in Oregon and so on to allow for more configurations and whatnot. So now there is this pretty advanced system, like was created in a very short order by Pablo and Marta, like with front end in Next.js, which I hate, but I wouldn't share that publicly with people like that don't really care about this. So like doesn't matter. But there's a fast API, by the way, backend. And then there's workers that use memory to actually gather all of this memory information. And now that allows us to do continuous memory monitoring. So if we have any regression that something grew in memory usage unintentionally, we will know about this. We can compare configurations for the same commit to see what is the overhead of PyDebug or what is the overhead of not having the global interpreter lock, which, if you remember, was one of the sort of reasons to accept or not the productionizing of the free-threaded Python, right? So like all of those recent changes in Python are being enabled by us actually seeing whether the performance is good enough. So now you can have not only this historical data archive that is allowing you to just see how things changed in time, but you can even see memory flame graphs like interactively, where if you have something that did regress, right? So for example, some particular benchmark now is using twice as much memory, you can click through and actually see what caused this allocation. So where this allocation differs from the previous commit. So this is extremely useful and allows us very quickly to identify where the differences in allocations are. So yeah, like this is not a user-facing feature for Python, but it is allowing us to see an entirely new dimension of resource usage that we have not been really tracking very closely before. And now we are, to the extent where already memorypython.org is being liked by core developers better than current speedpython.org.
Well, I mean, that's easy. That's a low bar. That's a low bar.
True. So after EuroPython, we will be essentially migrating speedpython.org into the same infrastructure as memorypython.org. So this name is probably a little short-lived. If you are listening to this, like, you know, some months after we recorded this episode, maybe there's no longer memorypython.org. It's only a redirect into benchmarkspython.org. And benchmarkspython.org is going to have like everything, right? Like both speed and memory usage, because you know, if you have one piece of infrastructure like this, you could also correlate, you know, changes in one and other dimension, because sometimes a memory price paid is such that the wall clock performance is better.
Well,
right?
I mean, that's very common.
It is very common, yes.
For instance, can you name one case? Just one case at random that comes to your mind when memory is a trade-off for performance.
Well, like
maybe you already said
caching, so memorization, like whatever, like all of those things were like.
No, but the one that you say this episode, the
Yes, exactly. Yes.
Because those bytecode copies take space.
Yes, right. But they allow us to avoid locking. Yeah. So that's
we can know how much we need.
Yeah, exactly. So all of this is clickable without you logging in. You can see all of this is public. You can play with this. There is a bunch of more functionality for core developers who do log in, but like publicly, it is already pretty cool. Like, you know, kind of we are gathering more information like day in, day out. So pretty cool. And I need to also mention that like this is running now like on Cabotage, like the PSF sort of like Kubernetes based sort of like micro Heroku, like whatever you would call it, which is like very cool to see. Like it is like an internal thing. Like you will not, as a Python user, like be able to just like use this. It's sort of like a tiny digital ocean inside your PSF. But for us, it's just like such an upgrade over Heroku, which we're like, you know, kind of even simple things like just having access to your logs for extended periods of time is just not a given.
Right.
And here, like, you know, like you have everything and everything just works like instant. It is just so performant, it's just so fast. So very cool that this is all staying like within the PSF infra. So like, and also it's no longer this super old style, you have a box, you know, just run some process on it, but it is in fact, you know, kind of Kuberneticized. So we have nice like redundancy and, you know, all of those like reproducible builds from Docker files and so on and so on. So like modern infra, but it is very quick. So I love it. So that's maybe not a PR of the week for me, but definitely something that is like a very visible chunk of work for at least our core developers. And hopefully is going to end up making Python better for you users, because we're not going to miss unnecessary memory consumption.
Right. All right, amazing. I cannot wait for it to show, benchmarks, because those squiggly lines will be a bit more fancy than the ones that because memory
usage is typically pretty stable. Yeah.
I mean, if you select only the weird, but it's mostly because the benchmarks that we have right now for memory are like the performance ones, so it's like not great because it's who knows what it's measuring. But if you select a bunch of ones like the heavy ones, like, you know, Queens, Richards, and body, and then you check JIT versus debug versus the other, then you can see something, especially if you do the relative view. But yeah, not necessarily enough performance, and it's not changing that much. So yeah, very looking forward for your changes. That's going to be
yes,
like paradoxically the biggest
I'm also looking
thing.
forward for that. Yes.
Right. All right. But now it's talking about like we have a lot of like things because we were late and we are pieces of garbage.
What's
going on
in CPython?
Right. Let me start with my typical section, but this time, actually, it is more celebratory than usual because we did it. We made it.
Wow.
We have arrived.
1
Yes.
million? Oh,
No, it's
different
even
thing.
better. It's 779. It's
Oh,
PEP 779. Criteria for supported status of free-threaded Python. This was approved by the steering council, and the experimental tag was removed from free-threaded builds even for Python 3.14. So this is a supported configuration right now. As users, you should feel encouraged to test free-threaded right now to see whether it makes your life better. It is very close to single-threaded performance and scales very well. I highly recommend you try it out. It is a new era for Python. Very happy to see this approval. And obviously, there is a ton of changes that are happening on that front the entire time still. And you should expect more. But it is, an area of huge amounts of development right now. I'm very happy to see this.
Amazing.
And speaking of like regular changes in free threading, Peter Victorian is working on making stable ABI for free-threaded Python also a thing that you can depend on. That effort is ongoing. So far, he added opaque PyObject to hide PyObject layouts from free-threaded builds so that you can start like thinking about some internals of CPython not being part of a stable ABI, and more changes are coming. On the other hand, some grows made new APIs for the free-threaded version of Python. In particular, PyMutex is now like a nice public C API to just check whether mutex is being held. There are blocking APIs for just locking mutex, but sometimes it is in fact helpful to just do like a check whether is this held or not, depending on the particular kind of design pattern that you're using.
Right.
Neil Schemenauer made quiescent state-based reclamation. It used less memory. I wonder if he used memorypython.org or not. But now, like, it is in fact using 15% up to 15% less memory in AsyncIO loads. So that's good. That's
very impressive.
Yes. Plus, more things are getting thread safety improvements. Like Peter and Debak made itertools.chain thread safe. Xuantong Huang made using atomic writes on heap queue operations, and Benedict Tran made more consistent use of mutex in hashlib. So all of those things make Python more thread safe and more performant while being thread safe. And speaking of performance, Pablo?
Yes, so our favorite person, the Shannon, the theorem maker, implemented a change that as part of the top of the stack caching in the JIT compiler, only integer operations are specialized for compact integers only. Mark Shannon, in his own words, says that using compact integers only and de-optimizing in the extremely rare case of no memory usage, I suppose he refers to the fact that when the integer is too weak, that doesn't fit the memory, or it needs to doesn't fit long or whatever, we can simplify the performance critical parts of the integer operations. Amazing. So Mark Shannon also made that the array stack items are replaced by a scalar for UOPs. That's the micro operations that we talked before in this podcast, which is a progress towards being able to copy and swap by simple register-to-register moves. So basically, this is to be able to optimize the bytecode templates, and so it goes to
this is all of this top of stack caching.
So the idea is that you don't need to spill in the stack, right? Like you just say, okay, here is a racks, and I just move to EX or something like that, right? Ken Jin contributed to only specialized arithmetic to compact integers, a lot of integers in this performance.
This is related.
Section. Yeah, avoiding crashes due to the GC running in the middle of long object functions. Wow, man, the GC running in the middle of things is a problem. Good that someone fixed that for the general case. All right. Kenjin also implemented automatic. Man, this is very cool. This is very cool. So Kenjin also implemented automatic constant evaluation of pure operations. That sounds very smart, but like the idea is that, in his own words, the main idea is that fully pure bytecodes, pure in this case is bytecodes that don't depend on global state, and then the same input that gives the same output. That's what pure means. So fully pure bytecodes can just run the body in the JIT optimizer, and this allows for automatic constant evaluation and propagation. What does it mean? Well, it means that if you are adding two constants, then the result is also constant. If you are dividing by another constant, then the result is another constant. If you pass that to another function, then that's what it means, propagation. It's very, very constant propagation is what an invalidation of the propagation. Like, for instance, you add a variable. Is that variable a constant? Can I prove it's a constant? It's always a constant. So that kind of optimization is something that the type checkers need to do as well. So it's easy to do. So this the idea of this is that this cuts down the code duplication, because we are already doing this by hand in other places. And also the amount of human error from manually writing constant propagation code. Again, this is because if you do it by hand, you need to say, well, can I prove that this is a constant? Yes, then I put it here. So the idea is that the G compiler, it will just basically trace it, and it will know, like, okay, this is a constant, I can reason about it, so you don't need to manually do it. This is very cool. And finally, Ken also eliminated degrefs for float operations in the JIT compiler, and this gives for micro benchmarks that uses floats, it gives a 7.5% speed up. Very cool. JIT compiler getting better.
Yeah.
But the JIT compiler is kind of like, this is very specific. Tell us some random shit.
Well,
Łukasz Langa.
I would like to tell you more about like new features of Python, but for now we are not in this great like time to add new features since we are working.
What do you mean? We have a big.
I know, but that is a rare exception, and there is.
We should make an extra episode about it.
There is another exception. Benedict Tran added math.signBit, which is a small function, but it is useful to detect negative zeros and negative infinites and negative nans. So that there is, in fact, already a new function in the math module for Python 3.15 that you're only going to see in October of next year. But I have a bunch of things that might just interest you. So they're more like curiosities or like, weird shit, as Pablo said. So Kumar Aditya put in a ton of work to make AsyncIO thread safe and efficient for the free-threaded build in Python 3.14. And now the design of how it works and, how all of those little pointers and avoiding locking work very well, which just happened to just very well coincide with what we were working on with external introspection. So he documented all of this in our internal docs. So if you're wondering how is this working internally right now, you can go over there to internal docs AsyncIO and read upon the design. This is very good. This allows us to share knowledge very efficiently, and it just shows how much work that was. So I'm pretty happy about this.
Trivia question, surprise question. Łukasz Langa is back. Łukasz, there is a bunch of things about hashes and whatnot, and infinities and negative infinities and whatnot. So now the question is what is the hash of zero, Łukasz?
The hash of
you cannot run it. Hash of zero.
The hash of zero cannot be zero because that's null.
It's already zero. Bad. Hash of zero is zero. What is the hash of -1?
-2.
Very good. Very good. What is the hash of none? Not a number.
I don't know if we have a special value for that.
Yes, it's very special. 0. What is the hash of infinity?
Also 0?
No, it's the 1, 2, 3, 4, 5, 6, the 6 first digits of pi. 3, 14, 15, 9.
Oh,
all right. And finally, what is the hash of minus infinity?
Is it minus pi?
Yes, but not full pi, but the 6 digits of pi. Yes, yeah. Nice, awesome.
Okay.
Yeah, now you know.
So why did I remember it wrong? That we cannot have 0 because it's
because I think you were confused by the -1 case.
Yes, the -1.
You were thinking about the -1 not being possible, and then probably you conflated 0 and -1.
Yeah.
But yeah, -1 is not possible because it's it's not. To be honest, I will have made the same mistake because you will say, okay, I know that -1 cannot be because it's the error code. So probably 0 cannot be as well because that's the success code. So like, wow, but the success code is fine because you will propagate success and that's fine.
I see. Okay, cool. All right.
I think that's where your confusion came from.
Yeah.
And the fact that none gives 0, I didn't knew that before I checked.
That is a little strange, but yeah, I accept it.
Yeah. All right. So that's it. Cool. So let's go back to the random shit.
Yeah, so like we are running a ton of external tooling to help us with the complexity of CPython these days. So a very important one, like we're going to mention it later, is the thread sanitizer. We're running that. And there's a bunch of others that we can also sanitize. But one that we had trouble setting up for quite a while was the undefined behavior sanitizer. Like this one's been flaky for a bit. Like the Pablo was running like a build bot with it, and it's it is a little bit of a chore. But now Peter Victorin made it so that this undefined behavior sanitizer is working as part of our GitHub Actions workflow. So if you make changes that are breaking UBSAN, you will be let know right away on your PR. And this already found some issues in remote unwinder object. I wonder who wrote that.
Whoop. Remote unwinder object. That sounds like some
Remote
cowboy.
debugging.c.
Yeah, no, impossible. No, it's actually for a provider. But yeah. Wow.
Yeah, and then we are, in fact, as we mentioned already, we alluded to that already, past the final beta. So now it's time for release candidate preparations. What that means is we are in this weird sort of space of time where we are in the space of time. That sounds weird. Like I'm being
the space of time. The space of time. It's technically correct, no?
Yeah, it's a period of time I wanted to say, but like space of time sounds weird. Anyway, like we're getting off track here. But we are before the first RC, after the last beta. So which is it? Like, is it still a bug fix release? Can you still fix bugs? Well, of course, but there are issues. You cannot just... Yes, issues with bug fixes. You cannot be any more like, kind of very willy-nilly about bug fixes because we have this contract that after the last beta, we will not touch the ABI anymore for a given Python version, which means you can now build extensions and publish them on PyPI for Python 3.14, and you should assume it's a contract given to you by the CPython core team that those C extensions will indeed work with Python 3.14.0 released in October and versions further, right? So, like the 3.14 editions further. So, because of this, we need to be a little careful not to make bug fixes now that actually are ABI incompatible. And to ensure this is the case, the sort of bytecode generated magic number is being updated in tests. As like every year we do this, there's this sort of ceremony of like, oh, before RC, you need to mark the magic number of the generated bytecode to the current number that we arrived at for 3.14. That number should not be moved at all for 3.14 from now on. So Hugo did that. So we are slowly moving towards release candidate. You can already feel that in the air.
We're close.
Yes, we're close. And speaking of which, Diego Russo is now also a co-owner of the JIT, marked in the repo, so must be true. But he is contributing to that thing. So I'm very happy to see like a lot of interest in the JIT.
Do you know how I find out about this?
Well, how?
Because I made my PR for fixing the trampolines and whatnot, and the file is called perf_jit_trampoline, and they added themselves like Savannah, Brand, and Diego added themselves the co-owner as *jit*. So they appear as co-owner. Well, I don't care. Just to be clear, I just don't mind. But like I made this like custom image of like Abe Simpson, like raising his fist at the clouds, and I took a screenshot of the co-owners just so it's clear like Abe Simpson was complaining about it. And Brand like just create a PR removing refining the rule, But that was it. Like he quoted my image and like he created the PR. So then I was like super scared. Like, man, I hope I was not like being I hope I was not being too violent with this. I don't mind at all this thing. But like no, of course he was absolutely fine. Like
Nice.
he's such a gentleman. But the problem of being a clown is that sometimes you over clown. So I was like, I'm over clowning. But then I saw Diego Russo and I said, okay, nice. Like the guys. You did it, Diego. You did it.
Yes, you did it.
We're talking about you, Diego. Yes.
So
All these people.
let's finish up with some actual bug fixes, huh?
All right, yeah, bug fixes. So Kumar does have a bunch of very cool things. Man, very good. So one thing he's doing is that he's making TSAN better. What is TSAN? It's thread sanitizer. Very important for free thread. So this is fixing data races in some interpreters under thread sanitizer, which is, very important. And there's a bunch because it's a not super explored area, unfortunately. As well as made in test concurrent features and test CAPI run with T-sanitizers.
Yeah,
Cool,
the more tests we
that
run
is
with
going to unveil so much shit.
Exactly.
And Sergey Storchaka, our good friend from Ukraine, made a number of changes fixing XSS in HTML parser, the function that has more CVs in the standard library, around comment and CData parsing. Hopefully this doesn't create more CVs. We will likely be batching another round of security releases later in the summer because this is a fix for a security release, of course.
So like this was actually like a little controversial in the sense that those changes in HTML.parser, they are a little larger than what you would normally want in a security release. But the problem is you couldn't fix just one of the 4 issues that like Sergey found and claimed success on improving security, because all of those 4 essentially are the same class of error. So if you already admitted that like, okay, there is a vulnerability around comment parsing and only fixed one issue with comment parsing, well, that would suck because that still leaves people vulnerable. So we decided to backport all of them all the way back to 3.9. This shouldn't really break any users, of course, like famous last words, but this is mostly around things that are invalid being treated as if they're valid, such that you can, with data that is insecure, in fact, like lie to a validator. So like if you would write a validator of user input with HTML parser, before Sergey's fixes, that was impossible because there was a way for the user input to circumvent the validator using HTML comments. Now this is impossible. So it's going to be a little bit of a larger change that the 3 people in Debian, Ubuntu, and Red Hat who actually backport all of those things will notice. Everyone else just should upgrade to a newer version when it arrives later in the summer. And with that, we are leaving to Prague just tomorrow, and we'll see you there. So thanks for listening to the episode right now, and hopefully there's going to be a next one for you right after the conference.
Thank you very much, people, for being with us here. Hopefully we have another filler episode for Europa. Who said that? Okay, sorry. But yes, thank you very much, and until the next time.
Until next time.
Bye!